दोनों जन गुड इवनिंग सर.
Yeah, good evening. Okay, so I think now we can start the session. So good evening, everyone. Welcome to the week 12 live session on the course titled Machine Learning and Deep Learning Fundamentals and Applications. So unlike the other weeks where basically I solved the weekly quizzes, so as because now we are at week 12 live session, so technically I should be solving the week 11 quiz, but as because the quiz is now live, so therefore by the policy of NPTEL, I cannot solve that particular uh, quiz as because it is not been evaluated yet. So therefore, what I will do in this particular live session is that I will take some practice problems based on convolutional neural networks that might be helpful to solve the questions that is there in the live quiz. And at the same time, as I already told in the last class that uh, majority of these algorithms, as these are related with the implementation part as well. So in this tutorial, I will be also implementing some of the neural network architectures that have been taught in the class. For example, you have seen that the basic CNN architecture, it started with LeNet. Then the next network that you have seen, that is basically AlexNet, then VGGNet, GoogleNet, ResNet, etc., etc. And till date, there are enormous amount of networks that have been proposed in the literature. So, however, we'll stick to the very basic ones that have been taught in the class. So we'll also will basically implement those networks in Google Colab platform, which basically uses Python as the coding language, and we'll be using Keras and TensorFlow to implement those models, and we'll also be using scikit-learn to see that what is the performance of the model in a general sense. So let us first solve some of the practice problems on CNN. So in the uh, first 1 hour, I will solve the quiz. I mean, the practice problems, and then in the next 1 hour session, I will be implementing the coding part in the Google Colab platform. Fine. So let us start the problem. So the first problem states that what should be the response dimension if an image of dimension. So the image dimension you can write in both the formats like 25 cross 25 cross 3. So here it is written that 3 cross 25 cross 25. So 3 indeed it means the channel, and this 25 cross 25 is nothing but height cross width. You can write either in this fashion, otherwise you can write in the standard fashion, that is 25 cross 25 cross 3. So the statement is the dimension of image. So image dimension is this one, and the filter dimension is given as, so filter dimension is given as 5 cross 5 cross 3. So you have an input image which is 25, 25, 3, and you have a kernel which is 5, 5, 3. Now what you have been asked to do is basically the convolution. This is the convolution operator. And then you have to find the output's shape. So now we know, as from the lecture itself, the shape of the output is basically governed by this equation. Output shape is equals to input shape minus kernel size plus 2 into padding divided by stride. And after all this, there is a plus 1. So this is the formula for output shape. If you convolve a kernel with a input tensor or input image. In this case, they have written that there is an image. Fine. So therefore, now let us plug in the values. So input shape is 25 because this is the height or width is same. So therefore, input dimension is 25. Kernel dimension is 5. So it is 5 plus 2 into padding. Now in the question, they have not been given any padding information and stride information. So if you encounter any such problems where padding and stride information is not given, so there you have to consider that padding is equals to 0 and stride is equals to 1. So therefore, by that logic, 2 into padding is equals to 0 and stride is 1 and then plus 1. So it is 21. Therefore, the output size is equals to 21 cross 21 cross 1. So therefore, this is the correct answer. Then the next question states that what should be the response dimension if an image dimension of 25 cross 25 cross 3 is padded with width 2. So in this question, now you can see that they have given the padding information. So padding is equals to 2. And rest of the information is same. So you can consider that stride is equals to 1. Because already we have seen that if you have been not given any sort of conditions, then you consider padding equal to 0, stride equal to 1. Now over here, they have given the information of padding. So you put 2 as because they have given over here that the padding dimension is 2. However, they have not given any information regarding the stride dimension. So we'll put stride equals to 1. Thereafter, now we have to find the output shape. So output shape is equals to, so your input shape is 25 minus your kernel shape is 5 and then 2 into padding. So here it is 2 by 2 into 2 divided by stride is equals to 1 and then plus 1. So you can see that 25 minus 5 plus 4 plus 1. So this 5 will basically cancel. So therefore, output dimension is still 25. Now, therefore, your overall dimension, overall convolution output dimension is equals to 25 cross 25 cross 1. So therefore, you can see that your input dimension was 25 plus 25 cross 3. Effectively, your height and width of the image was 25 cross 25. In the first question, you did not use any sort of padding. So therefore, you can see the convolution dimension, the output of the convolution, its dimension is reduced. However, they have put a padding of 2, which is why even if you do the convolution, your output dimension is still the same. So the main necessity of padding is basically you put a proper padding so that your output dimension is same as the input dimension. And this is what you will see in the coding part as well. So in coding, you will see that there is a term that called padding equal to same. So padding equal to same basically ensures that you pad some value such that your input dimension is same as the output dimension. So then it will find that what should be the padding value. So over here, 25 plus 25 plus 1 is the correct answer. Okay. So the next question states that an RGB input image, red, green, blue input image is converted into a matrix size 257 cross 257 cross 3 and a kernel or filter size of 7 cross 7 cross 3 with stride equal to 2, padding equal to 3. So now they have given both stride information and padding information, which is used for 2D convolution. So what will be the output size? So similarly, I can write that output dimension is basically your input dimension minus kernel dimension, that is 7, 10 plus 2 into padding. So padding is equals to 3 over here, then divided by 2 and then plus 1. So which turns to be 1 second. So this is 128 plus 1. So therefore 129. So now you can understand that for one dimension you have got 129. So this for this dimension also, if you calculate, because this is same. So therefore overall output shape after convolution is equals to 129 cross 129 cross 1. So therefore you can write it like this. Okay. So the next question states that the primary reason for adding pooling layer is. So now let us first find that what is pooling layer. If you have seen the CNN architecture, the CNN block typically looks like this. Let me see whether I can paste any picture over here or not. Yeah, see, we have taken an example of average pooling over here. So in case of average pooling, let's say you are doing average pooling with kernel size 2 by 2 and you have put a stride of 2. So how will it work? So first you place a kernel of 2 by 2 shape. That is what we have put over here now. Then you will do average of this thing. So average of 2, 3, 5, 6 turns to be, so this is basically 1 upon 4, 2 plus 3 plus 5 plus 6. So this will give you 4. So this will give you 4. So therefore, you will put the value over here. In the next phase, as because this is stride 2, that means you will be sliding this particular window by 2 units. So therefore, it will be shifted to this side, right? It is due to that you have put stride 2. That means it will be first shifted from this block, then it will be shifted from this block. So again, you calculate the average and you put it over here. Then it will be shifted vertically as well by 2 units. So therefore, it will come over here. Then you put the then lastly, you shift this again by 2 units. So it will cover this. And then you take average and you put it over here. So you can see that initially you had a matrix size of 4 cross 4. And after pooling, the size has become 2 cross 2. So that means what pooling layer in general, what pooling layer does is reduces the size of the activation map. So over here, this particular matrix is often called as activation map. So it reduces the size of the activation map. At the same time, so over here in the small, so in the window, this particular window, what we are doing, we are summarizing the information. We initially had 4 different values. Now we are summarizing the information by taking an average. So therefore, within the kernel of the pooling block, we summarize the information by taking either average or maximum value. So in average pooling, it will be averaged in case if we take maximum value, so that time that is called max pooling or MP. Okay, so now let us see. The primary reason for adding pooling layer is increase the feature map size. So this is incorrect because we can see that initially your feature map size was 4 cross 4. So activation map, this is also called feature map as well. So there are several nomenclatures are there. You will see as you go along with the deep learning lecture series. So it does not increase the feature map. Rather, it reduces the size of the feature map. So as the size is reduced, it automatically indicates that computation in coming layers or the subsequent layers is also reduced. So this could be point number 3. So reduced computations in the subsequent layers, because it is true, because you see initially you had a bigger matrix, you have processed it using average pooling, therefore your matrix size is decreased. So in the subsequent layer, if you apply some other transformation or other formulations, so as because the number of elements in the matrix is less, so therefore number of multiplication and addition will also be less. So therefore the number of computation will drastically reduced. So therefore option B is correct. Then to produce activations that summarize filter response in local windows. So this is what point 2 refers, that within the local window. So this local window basically refers to the kernel of pooling, whether it is a average pooling or max pooling. So this is the local window that basically means the kernel of the pooling layer, be it an average or a max pooling. And what we are doing, we are summarizing the response within the kernel size or within the local window size of the pooling layer. So therefore, this is also true option. So the last option states that both B and C. So therefore, option D is basically the final correct answer for this particular question, as it eventually reduces the dimension of the activation map or feature map, and hence subsequently reduces the computational complexity in the late coming layers. And additionally, what we are effectively doing within the kernel size or within the local window that have been provided in average pooling or max pooling, whatever it is, we are basically summarizing the information within the local window shape by taking either average or maximum, etc. Okay. So choose the correct. I think transfer learning has not been taught. So therefore, I think I should omit this. Yeah. So the next question states that advantage of ReLU over sigmoid and tanh is. So let me first draw three of the activation functions. So this is sigmoid, this is tanh, and this is ReLU. So ReLU for the negative half side, it is 0, and the positive side, it is with unit slope. So that is y equal to x, and over here y equal to 0. On the other hand, sigmoid at zero, it has a value of 0.5, and if you increase the value, it will reach 1 asymptotically. And if you decrease the value, it reaches 0 asymptotically. Asymptotically means if you put infinity plus infinity, then you will get sigmoid output equal to 1. And if you put minus infinity in the sigmoid equation, so sigmoid, so sigma of x is nothing but 1 divided by 1 plus e to the power minus x. So if you put plus infinity, so e to the power minus infinity means 0. So that means 1 divided by 1 equal to 1. So if you put plus infinity, you will get 1. If you put minus infinity, e to the power minus of minus infinity means 1 divided by 1 plus infinity. So therefore 1 divided by infinity will give you 0. So that you can see over here also, that if you decrease the value, when it reaches infinity, it will touch 0. So that means absolutely, in absolute terms, there is nothing called plus infinity and minus infinity. So therefore, it takes huge amount of time to reach plus 1 and minus 1. So this sort of approximation is called asymptotic approximation. This approximation you have also seen in Boyle's law as well, that PV equal to constant like that. So those parabolas are basically asymptotic approximation that we have studied in probably class 10th or something. Okay. Then, so far as the tan H is concerned, tan H has also similar shape, but the range is different. So tan H is range in between +1 to -1. And this looks like this. Again, asymptotic approximation is there. When it reaches plus infinity, it will reach +1. When it reaches minus infinity, its value is -1. So this is how tan H looks like. Now, what are the issues with sigmoid and tan H? So if I just write sigma dash of x, that means I am taking derivative of this sigmoid function. So I am just writing it directly. I have proved this particular formulation in uh, week 1 live session. You can visit week 1 live session that is there in YouTube, and then you can check this particular derivation. But this is a standard derivation that you can remember, because many of the problems that you will see in final exam may relate with this particular formulation. So directly you can write this particular equation. So that is, if you take derivative of sigma, so you will get this equation. So let's say, let's x is very high. X is very high. So we know that when x is very high, sigma of x, approximately it is 1. I can write approximately equal to 1, because you can consider that sigma you have put very high value. So 0.9999999 something will come. So I can write it as sigma of x is approximately equal to 1. So what will happen to sigma dash of x? That we have to see. So sigma dash of x will be sigma of x, which is 1, once again, which is 1 multiplied with 1 minus 1. So that means output will be equal to 0. So that means when x reaches to infinity, then your sigma dash of x will become 0. This is one condition. At the same time, when x reaches minus infinity, that means you get very small value, then you can write sigma of x approximately equal to 0. That we can see from this particular figure as well, that if you put x value is very nominal, then what will happen? Sigma x will reach 0. Approximately it will be equal to 0. So now what happens in case of sigma dash of x? Sigma dash of x is basically 0 multiplied with 1 minus 0. So again, it is 0. That means when x reaches minus infinity, sigma dash of x becomes again 0. So these are the two important properties that you can see in the sigmoid function. And from the diagram itself, I can prove this particular thing again, that whether the derivative is 0, that means derivative is not yielding any value. So see, in this region, sigmoid is linearly increasing. But when you increase the value, you can see that hardly there have been any changes. So very minute change as you go along this direction. So therefore, if you take gradient from this point to this point, the variation is very small, as because your delta y is very nominal. So therefore, your gradient is almost equal to 0. And that is what you can see from this equation and this equation. So what problem it basically arises is, you know that Wn plus 1 is equals to Wn minus eta del L by del W. Now this gradient, when you calculate this gradient with respect to the calculate of gradient of L or loss with respect to the weights, there is a chain rule associated with del W. So the chain rule includes this sigmoid term. And if it includes sigmoid term, you can see that sigmoid derivative will come as this. And if you put high value and low value, whatever value will put, your gradient, your del L by del W will reach, del L by del W will reach 0. So that means effectively the multiplication of these two terms will vanish to 0. So what will happen? Wn plus 1 will be equal to Wn. So that means your learning will stop. So this problem is often referred as vanishing gradient. Vanishing gradient. Why vanishing gradient? Because del L by del W reaches to 0 if your x or the input of the input argument of the sigmoid function reaches either very high value or very low value. Same thing happens over here as well. You can see that when you take derivative of tan h, you will also come across a kind of similar representation. But from the graph, if you can see, as we have taken an analogy from the sigmoid curve as well, if you increase the value in this particular region, you see that the change or the derivative is very small because there is very minute changes. Same as well here as well. So if you take derivative continuously, you will see that there have been any changes. So which also refers that the derivative output is equals to 0. So that means the del L by del W will reach to 0. And again, it will create vanishing gradient. Vanishing gradient. But now let us see what happens in case of ReLU. So ReLU in this particular zone, if you increase, so the function is y equal to x. So you take derivative, that is dy by dx. It will be 1. Whatever may be the value of x, x may be infinity as well. I mean infinitely large as well. Even if you take derivative, the derivative will yield value equal to 1. So that means your gradient will not vanish, at least for this region. Over here, so the value itself is 0. Over here, so the value itself is 0. So even if you take dy by dx, it will be 0. For negative half, for the negative part, I am not bothered. But as far as the positive part is concerned, in both of these cases, if you increase the value of x, your derivative was becoming 0. But in case of ReLU, you can see if you take derivative, whatever may be the value of x, however x is large, so your derivative output will be equal to 1. So that means your gradient will not vanish, at least for the positive half part of the ReLU function, which was not there in case of sigmoid and tanh. So only in the linear region, you were getting some sort of gradient. So over here as well in this region, you are getting some sort of a gradient. But as you go along in the positive direction, if you increase the value of x, the derivative is becoming 0. And the same thing can be observed in the negative region as well. So in both tanh and sigmoid, there is the main problem that vanishing gradient is an inherent uh, problem in both of these activation functions. However, in case of ReLU, we can see that at least in one half, we are able to avoid the problem of vanishing gradient. Okay. So now, based on this discussion, we'll basically solve both this question. The first question states that advantages of ReLU over sigmoid and tanh. So advantage of ReLU over sigmoid and tanh is low computational requirements, because you can see that your dy by dx, when you calculate the derivative is very simple to calculate in case of ReLU. But if you see the derivative expression for sigmoid, at least, you can see that the form is not that simple, because you have to incorporate again. If I just write this particular thing in this fashion, so sigma dash of x is nothing but 1 divided by e to the power minus x, 1 minus 1 plus e to the power minus x. So this is the form of derivative of sigma x, or the sigmoid function. So this is quite cumbersome. So therefore it is computationally intensive than this one. Over here, whatever you put, you get derivative equal to 1. So therefore, ReLU is computationally less burden. ReLU has computationally less burden than sigmoid and tanh. The next one states that elevates the vanishing gradient to some extent. So that is what we have already discussed, that for the positive half part, for this part, the vanishing gradient can be avoided. For this part, still the vanishing gradient problem will be there. So therefore, to some extent is the correct statement. Then backpropagation is simple. So backpropagation, you see, backpropagation again, it is basically a derivative of this option. So in backpropagation, what we have to do, we have to calculate the gradient. Gradient means we have to do the differentiation. So again, you see, you have taken differentiation of sigma of x. You got a very sort of a difficult expression, rather than that you have got in ReLU expression. In case of ReLU, the gradient is simple one. However, in this case, you have got a pretty strange response. So therefore, the backpropagation is quite simpler in case of ReLU, as because the derivative is very easy to solve. However, in case of sigmoid function or tanh function, the derivative is quite difficult to compute. So therefore, so as far as the analytical computation is basically concerned, so backpropagation is also simpler. So therefore, as because all of these options are correct, I can write all of the above is the final answer. Okay. So the next question states that what of the following activation function has no gradient in negative responses? So you can see that your y is equals to 0. Over here, y equals to 0 in case of ReLU. So whatever may be your value in case of so y equal to 0 when x is less than 0. So this is the form in case of ReLU. So as because your ReLU output itself is 0 in the negative side. So therefore, there is no point of having any gradient in that particular region, in the whole region. So that means dy by dx will be equal to 0. But in case of sigmoid, you can see in this region you have, in the negative region, for example, in this region, you still have some sort of gradient. As you go along in this direction, the gradient subsequently vanishes. Over here as well, in the negative region, you have certain gradient in this, in the first few regions. But as you go along, uh, decreasing the value of x, the gradient subsequently vanishes. So therefore, sigmoid is an incorrect option, because you can see in the negative region, so you certainly you have some sort of gradient. Tan H is also incorrect, because again over here you can see that you get some sort of an gradient in this particular region, subsequently vanishes to 0. ReLU, on the other hand, ReLU does not have any response in the negative side. So therefore, subsequently the derivative will also be equal to 0. So therefore, it has no gradient in the negative side. And what about absolute? Absolute means y equal to mod x. Now mod x has this kind of shape. So immediately you can calculate the slope over here. So over here the slope is 1. Over here the slope is -1. So therefore, the gradient exists in both the direction, and specifically in the negative direction. So therefore, absolute is also the incorrect uh, option. Okay. So the next question states that how many convolution layers are there in LeNet-5 architecture? You will see similar sort of questions are also been there in week 11 live session. Sorry, in week 11 quiz. But these sort of questions are kind of memory based questions. If you can remember all the architectural details about the existing neural network architectures, such as LeNet, VGG16, then you have AlexNet, GoogleNet, ResNet, etc., etc. Then you can immediately answer those questions. But as because in many of the cases I forgot the uh, architectural details, so that is why I just have pasted the formulation of the LeNet as well. So in case of LeNet, you can see you have got, this is the input. This is fast convolution layer. Then this is fast pooling layer. Then second convolution, and then second pooling layer. And over here, what you have done, you have flattened the data. So initially you had a tensor. Now you have flattened into one-dimensional vector. And then subsequently you have added, these are also called the MLPs, that is multilayer perceptron. Already we have seen in week 10's lecture that what is basically meant by multilayer perceptron. It is basically a collection of artificial neural networks or the singular perceptron models. Single perceptron models. So how many number of convolution layers that we have? That is the question. So we have convolution layer 1, convolution layer 2. So therefore, we have a total of 2 convolution layer in LeNet-5 architecture. Okay. So again, another question based on some memorization trick. So this question states that what is the architectural difference between VGG and AlexNet? So if you see the original paper of AlexNet, AlexNet was basically trained on, 1 second. AlexNet was trained on two parallel GPUs, which is NVIDIA GTX 580 3 GB GPUs. So this was the hardware specification that they had used. What they did, as because they had two GPU cards, so they created two different pool of structures. So this pool, the upper part was computed using GPU 1 and the lower part was computed using GPU 2. And after that, whatever data was coming, so they have been concatenated in the last stage for the classification. So these are the fully connected layers or MLP. So you can see in case of AlexNet, there are two streams, right? However, in case of VGG16, you can see the data. This is the input data. This is called retinal image, or in medical terms, this is called ophthalmoscopic images. The retina images are basically called ophthalmoscopic images. So you feed this ophthalmoscopic image into the neural network architecture, which is basically the VGG16, and you can see the data is flowing through a single stream. So it is a single stream architecture, right? But in case of AlexNet, you had two streams. This is stream 1 and this is stream 2. This 1 and this 2. So therefore, now let us start solving the question. What is the architectural difference between VGG and AlexNet? The architectural difference is basically that how many streams are there to process the data. So over here we can see there is a single stream data, single feature extraction stream. This is single feature extraction stream. However, we can see in this particular case, we have two stream feature extraction. This is AlexNet and this is VGGNet or VGG16 in this particular case. So therefore, VGG16 has single feature extraction stream and AlexNet has two. This you can remember because obviously this is an architectural details. So there is no intuitive part. You have to remember that how AlexNet was formed. That's it. Okay. Question 8 states that if CNN filters no bias of size 3 cross 3 are employed for transforming an image with 3 channels into 64 responses. That means kernel size is equals to 3 cross 3. They have mentioned that no bias. Then what we have, kernel number or number of kernel is equals to 64. And this is applied on three-channel image. So therefore, I can write effectively kernel dimension is 3 cross 3, but we have to replicate for three-channel images. So therefore, I can write 3 cross 3 into 3. So this is the kernel dimension. So if we look at this, this is your kernel. This is how kernel looks like. 3 cross 3 cross 3. So how many elements will be there? That means a total of 27 elements will be there, as because 3 cross 3 cross 3 is the dimension of the tensor. And how many of such filters you have? So such that you have 64 such filters. So that means total parameter is equals to 3 cross 3 cross 3. This is for a single, and we have 64 such filters. So therefore, this is for all 64 cases. So this is your total parameter, which turns to be 1728. Okay. If max pool kernels of size 3 cross 3 are employed for transfer. So the main point is CNN basically needs learnable weights, because that is what you are learning. So this each and every entries you are basically learning. So these are learnable weights. So CNN is learnable layer, as we have learnable weights. So next question states that if max pool layer is of 3 cross 3 size employed for transforming an image with 3 channel into 3 responses, how many weights do we need? In case of max pool, we know that if you have a, let's say, image like this, and this is your uh, max pool kernel, and let's say you have certain values like 8, 9, 0, 1, 2, 3, 4, 5, 6. So what max pool does, max pool goes to a max pool sees a specific part of the input image, then finds what is the maximum value, and then it will put that maximum value. Then based on whatever stride you put, if you put one stride, then it will again see this particular region. Then again it will keep the maximum value. So that means there is no sort of learning that we are doing. We are just finding the maximum value. So therefore, in case of any pooling structure does not need any learning mechanism. We are just either finding the maximum value or calculating the average in case of average pooling. So therefore, we do not need any sort of learnable weights there in case of any pooling layer. So how many weights needed to be learned in case of max pooling layer is actually 0. Because in case of max pooling and in case of average pooling, we generally uh, do not need to learn anything because we are just finding a operation that is either maximum value or average value. Fine. The next question states that in inception block, the input transformation is processed through how many parallel channels? So over here, I have actually kept the image of inception block. So this is basically the so we can see in case of inception block, this was the previous layer output, and then you pass that particular tensor. Let's say the tensor has a size W cross H cross C, and then you pass this tensor through 4 different pathways, parallel pathways, the 1, 2, 3, 4, and they subsequently extract something. So this is output 1, this is output 2, output 3, and output 4. And at the last stage, what you are doing, you are taking concatenation. So that means output 1, output 2, output 3, and output 4. So this particular operation is called depth wise concatenation. So how many parallel channels that we can see? So we can see 1, 2, 3, 4 parallel channels in case of uh, the inception block. And in inception block, the processed input information is combined using which operations? So this was the input W cross H cross C. Then we pass it through the inception block, which processes this particular data, that W cross H cross C, in 4 different pathways, parallel pathways. And then at the end, it produces output 1, output 3, output 1, 2, 3, and 4. And subsequently, they are concatenated to create a final output, which is the output of the inception block. So this is O. So the operation that we are doing, that is called concatenation, or to be very specific, this is called depth-wise concatenation. So let us see. So the combining using which operation? Sum, this is incorrect. Multiplication, incorrect. Concatenation, this is the correct option, and none of this can be eliminated. Okay. Okay, so with this, we have uh, solved the practice problems for week 12. And now let me just upload the slides as well, and then we can Okay, fine. Okay. So now let us start with the coding part. So I will share the uh, notebook files as well in the uh, GitHub link and the GitHub link as well. So we have studied the convolutional neural network architectures, and specifically we have studied some of the state-of-the-art architectures like LeNet-5, then VGG16. Then we have also studied ResNet, and we have also seen Inception neural network architecture, all which is also commonly known as GoogleNet. So now let us simulate LeNet-5 architecture, and we'll be using the MNIST digit dataset. MNIST digit dataset already you have seen in week 2 live session. I have shown you the basic handling of the dataset in using PyTorch, TensorFlow, Keras, etc. So there I had taught you how to deal with the MNIST dataset, then Cypher10 dataset, IDs dataset, etc. So we'll be using the MNIST dataset to train our model or to train the LeNet-5 architecture. So a couple of things that you should remember when you actually do simulation in Google Colab. So let me just zoom in. So in Google Colab, you see there is a button called runtime. So runtime in Google Colab specifically provides you a very good functionality. Yeah. Google Colab basically gives you the functionality of accessing the uh, online GPU. So that means even if you do not have a high-end computer at your side, you can readily use a state-of-the-art GPU architecture or a cloud GPU. If you try to install Jupyter Notebook in your system and then you do this simulation, and let's say if you want to train a model with very huge data set, if your machine is not, if your machine means if your laptop or desktop is not that much equipped with a good hardware resource, that means it is not equipped with good amount of RAM, it doesn't have any GPU card, then it will take a substantial amount of time to train the model. So therefore, Google Colab came with an innovative approach that they provide a online or cloud GPU server, and then you can connect your Colab notebook with online GPU, and then you can run the code in online. So therefore, you do not need any sort of GPU requirement at your side, as because you are basically accessing the cloud-based GPU. So this is what cloud computing, it basically facilitates the cloud computing uh, thing. So go to change runtime type and then select GPU. So with a very basic Colab, you will get only these three type of resources, that is CPU, T4 GPU, and TPU. TPU is basically named as TPU basically referred as tensor processing unit. So if you purchase uh, a higher end version of Colab, so that is Colab Pro or Colab Pro Plus, with a cost of Colab Pro basically comes with a cost of 2000 rupees per month, and Colab Pro Plus basically comes with a cost of around 6000 rupees per month. Then you will be able to access these two GPUs, that is A100 and L4 GPU. But T4 GPU also works very fine. So let me hit save. So now there is a button that is called connect. So you can press this connect button and you'll see that now it is trying to connect your Colab notebook with cloud GPU. And when this yellow button will become green. So that means now it is being connected. And you can see that the moment it has been connected with the cloud service, now you'll be able to see all the specifications. So you can see that GPU RAM is 15 GB, disk size is 112.6 GB, and system RAM is 12.7 GB. So that means you have a cloud GPU, you have a cloud RAM, cloud GPU RAM, simple cloud RAM, and a disk. So now let us import the libraries. So NumPy is basically used to do any sort of array operations. Matplotlib is used for to plot something, to plot the data. Then we have already taught, we have we have already seen what is basically meant by confusion matrix. It is basically taught in week 1 live session. So we need confusion matrix to see the performance of the model, that how well it has been able to classify between the target labels and the predicted labels. And then comes the main packages that basically helps you to construct the deep learning architecture. So this is basically TensorFlow. So I'm importing TensorFlow as TF. Then from TensorFlow.keras.dataset, I need MNIST dataset. So I am importing the MNIST dataset. There are two type of neural network formations that you can see in TensorFlow. One is sequential API and another is functional API. So for this particular case, I will be using sequential API. So that means sequentially I will add the layers. So therefore I'm importing sequential, and then I'm importing all the necessary layers, that is con2D, average pooling, flatten, and dense. So dense means the MLP layers. And at the same time, I need the categorical. I have to import two categorical, which basically converts the what you call the labels into categorical variables. Because already we have seen in SVM lecture that the label should be categorical in nature. The type of the label or type of the data for the label should be categorical. So hit run anyway. Okay. Now we have to load the MNIST data set. So I have to load the training set. So X train means the training images, Y train means the corresponding label. And correspondingly, we have to also load the X test and Y test. So that means X test is the data in the test set and Y test is the label in the test set. And what I have to do, mnist.load data. We have already imported the mnist dataset from tensorflow.keras.dataset. Now to load that data, I just need to call load data, load underscore data. So then I'm normal. After that, what I am doing, as because these are grayscale images, the image value, the pixel values are in the range of 0 to 255. So I am just normalizing all the values in between 0 to 1 by dividing with 255. And I want the output to be float. So therefore, I'm typecasting the variable into float32. So let me just show you one by one. So that would be very easy for you to understand. So let me just hit this one first. So now I can print x train dot shape. So you can see that your x train dot shape has 60,000 images of shape 28 cross 28. Now let us see what is the shape of y train. It should be 60,000 only, because for each of the sorry, y is small in small letter. Yeah. So you have 60,000 images. all are of shape 28 cross 28, and for each of the image, you have the corresponding label. So as because you have 60,000 images, so 60,000 labels. Very clear about it. So I can plot the image as well. plt.im show x train 0 plt.label is y train dot show. So you can see I can also write CMap equals to, yeah. So let me be more specific. Label is I have to typecast this str. Yeah, so you can see that I'm plotting the first image, which is an image of 5, a handwritten digit, and that digit is 5, and the label is also 5. Let me be very clear about that. So you can take any sort of index. So let's say you can take index 10. Let me see what is there in index 10. So in index 10, label is 3, and you can see there is an image of 3. Now let us try to see how the values look like. So I want to see that how the values look like. Show data. So now you can see the minimum value is 0, and the maximum value it is basically ranging from 0 to 255. So you are getting values in between 0 to 255. So maximum value over here is 254. Now what we want to do, we want to normalize this data. We want all the values to be in the range of 0 to 1 instead of 0 to 255. So what we will do, we will divide with the maximum value. Therefore, if I just do this, and then let's say print again x train 10. So initially when we uh, saw the data without normalization, so that time we saw that the data ranges from 0 to 255, and the maximum value is 0, and the maximum value is 254, and over here the minimum value is 0. Now we want all the values in the range of 0 to 1. So therefore we are dividing every value with 255. And then again we'll see the same data after normalization. So it should be over here we are getting 1, 166, 254. All the values should be in the range of 0 to 1. And they will be float type. So that means they can take decimal point values. Now let us see. Yeah, so now you can see that the values are in the range of 0 to 1, and it can take the decimal point values as well. And if you want to see the image again, image will not be changed actually because you are just scaling up the values. So therefore, effectively, your image is same, but the values are in the range of 0 to 1. So fine, we have done all the process that I have just broken into pieces and just showed to you. Now we have to create the model, that is the LeNet-5 architecture. So how to create the model? So you can start with this model equal to, as because we'll be using sequential method to create the model. So that means sequentially one after another will be uh, putting the layers. So over here you can see that let us just try to see this architecture first. We had an image. So this is the input image. We have first convolution layer. In the first convolution layer, we have 6 filter and filtered shape is 5. Stride is 1, padding is equal to 0. So we have to specify everything. So now let me go to the model part. So con 2D, 6 means this is number of filter. Then kernel size is 5 cross 5. Activation, to avoid the vanishing gradient problem, I have kept ReLU, and the input shape is 28 by 28 by 1. And you can see that stride equal to 1, padding equal to 0, it is mentioned. And the stride equal to 1, padding equal to 2 is basically uh, by default thing that we can consider. In the problem also, I told you that if any information is not given, then by default, the padding is used to be can be thought of 0 and stride can be thought of equal to 1. So this is how we are putting the first convolution layer. Then we are putting the average pooling layer. So average pool 2D and the size of the pooling layer is 2 by 2. Then the next layer. So in the max pool, you can see that average pooling has filter dimension 2. In the next case, we have 16 filter, 5 shape is 5 and stride is 1, padding is 0. So therefore, again, filter number is 16, kernel size is 5 cross 5 and activation is real. Then after that, we again have the average pooling layer. Then what we have is the flattening layer. So that I have also shown in the yeah. So we had first convolution layer, we had first pooling layer, second convolution layer, second pooling layer. Then we need to perform the flattening operation, which will flatten this tensor data into one-dimensional representation, right? So that is what we will do over here. Flatten, and then we will put the dense layers with 400 neurons, 120 neurons, 84 neurons, and the last classification layer. So 120 neurons, 84 neurons, and 10 neurons. I have skipped that 401. So I can write 400 here. And all are activation ReLU. The last one has to be softmax because I want to know that the image belongs to whichever class. So softmax will give me a probability distribution. And from the probability distribution, whichever class index has the highest probability, I will assign that the image belongs to that particular class. And with this, my model is now completed and I can see the model summary. So now you can see that this is your model summary. And this is the total number of parameter. We already have calculated total number of parameter in this particular question. Here, this is the same way you calculate the total number of parameter in KDAS as well. So they have calculated parameter for each of the layer. So like this one, then see average pooling. Already in this question, all of these questions are related with the coding part. So it was talking about max pooling. So how many learnable weights were there? I already told specifically that pooling layers does not require any weights. So therefore weight equal to 0. So that is what you can see in the, that is what you can verify over here as well. Average pooling layer has parameter equal to 0. So that means you require no weights in any of the pooling layer, be it an average pooling, be it a max pooling, global average pooling, whatever it is. Flatten layer also, on the other hand, it does not require any parameter. And again, over here also, average pooling layer does not require any parameter or weight. Now we need to train the model. So before training the model, we have to compile the model using the command that is model.compile. We need to put the optimizer. In the last lecture, I have talked about how optimizers basically works. We can use momentum optimizer. We can use nestor accelerated gradient optimizer. But in majority of the cases, in the last class also, I had told that we specifically use Adam optimizer because Adam tries to converge faster than any other uh, cases. But it sometimes it is case specific. You have to perform you have to check with the other optionalities like RMS prop, NAG, etc., etc. And the loss is categorical cross entropy and metric that will be following, that is accuracy, because this is a classification task. So we need to focus on that how much accurately you are able to predict using your CNN architecture. So after compiling the model, now you have to fit the model with the training and validation data. So you fit with X train, Y train. You train the model for 10 epochs with a batch size of 128. So that means you do not feed all the 60,000 images at a time. You feed 128 chunks of data in each of the iterations. And then you have the validation split of 0.2. So that means you have 20%. You are keeping 20% data from this X train and Y train to validate the model, to see whether you are getting any sort of overfitting or not. So with this, now let me train it for, let's say, 20 epochs. And then we have to wait for some time to train this particular model. So you can see that the training has been started. And you can see initially at iteration at epoch 1, the validation loss is very low. And validation accuracy is 96%. Right. So already I think we have reached epoch 20. So now we can see the accuracy and loss plots. All of the loss plots and accuracy plots that we have seen in the week's lecture, now we can generate it by our own. So you see that there is some sort of an overfitting, right? You have very small overfitting. This you can actually, yes, Jyoti, I think, has some query.
Sir, I could not see your demo.
Sorry.
I don't see your demo which you are showing.
The screen is not visible.
Yes, sir.
So can you see the card? Accuracy and validation accuracy card. Can you see it?
No, sir.
Uh, are you able to see, Prabha? Can you see the
Yes,
screen?
yes, yes, I can see.
Can you see the graphs as well?
Yes.
Okay, so
No, sir.
probably at your side, Jyoti, probably at your side, there is a issue of internet. So anyway, I will upload the video. You will be able to see it because I think there is an internet issue. That is why you are not able to see the screen.
I am done for the questions which you provided.
But I think for others it is visible, so might be some internet issue. But anyway, I will upload the uh, video in YouTube. You can check it from there as well.
Jyoti, once you can sign out and again sign the meeting. Check if this app works.
You can rejoin again and then please check that whether you can see the screen or not. Okay. Okay, so the point that I was talking about is basically so the training accuracy. You can see that it is 99.70% and the validation accuracy is 98.75%. So therefore, very minute difference. So even though you can see in the graph, it seems to be very large one, but as far as the value is concerned, you can see that almost sort of similar response, right? So this is, even though it seems to be an overfitting, the values does not suggest so. If I just if you train it for, let's say 100 epochs or 200 epochs, you will see that this issue is quite mitigated. As because I am training the model for very small number of epochs, that is why this is also prevalent. Otherwise, it would have been gone. So there was no such gap was there. And this particular image dataset is very easy to classify. There is no much skew in the dataset. But the main motto for this particular simulation is how to create the model. So as because we are using sequential format, you can sequentially add each and every layers. So this is the first convolution layer, first pooling layer, second convolution, second pooling, flatten layer, dense layers, and subsequently the final classification layer with softmax activation. Okay. So now this is all about the training process, how the card basically looks like. Now we have to see the testing result. That is very much important because from the testing result, you will be able to understand how your model performs on the unseen data. That is very important. So how to do that? So you have the trained model, which is named as model, and the function is model.evaluate. You feed X test and the corresponding labels. So it will give you test loss as well as test accuracy. And you need to print the test accuracy to see that what amount of accuracy you have achieved by training the LeNet-5 architecture with 20 epochs. And then we will plot the confusion matrix. So you can see test accuracy is quite well, 98.94% accuracy. So that means this is performing very well. And this is the confusion matrix. However, let me just go to the next part. And this basically will show the correct representation of the confusion matrix. So you can see that in in zero class 0, you have a total of 975, 976 plus 4. So that means 980 data. You have a total of 980 data in the test set for class 0. Out of all those 980 samples, you are correctly classifying 975 samples. You are doing misclassification in this part your original data is 0, but you are predicting it as 1. Your original data is 0, you are predicting it as probably 6, 7, something like that. So this is the true positive. If you can recall, this is the true positive. All these things, all these off diagonal elements, these are false negative. These are false negative. And along this axis, you get false positive, and subsequently you can calculate the true negative as well. That this type of example we have also covered in week 1 live session. So if you are not able to recall that, you can again see the lecture. So this is the confusion matrix that looks like, and the main fundamental thing is here that your off diagonal element should be as minimum as possible. If you have larger amount of off diagonal elements, so that means you are not able to classify many of the samples correctly. But over here you can see that out of 980 samples, 975 samples are correctly classified. So that means you are able to, you have done good classification. Over here also you can see for class 1, you have 1135 number of samples, a total of 1135 number of samples. Out of all 1135 number of samples, you are just doing misclassification in 3 cases. Rest of the cases are correctly classified. Can you see the screen, Jyoti, now?
Yes, sir.
Okay. Okay. Okay, so this is all about the confusion matrix. You can check that how many correct classifications you have done, how many misclassifications you have done from the confusion matrix. Now I want to visualize the test results, that you feed an image into the trained model, then model will give you some prediction. So you have predicted output, and as well as you have true outputs as well. And I want to see all of them together. And how to do that? So this is where I am doing this. So what I am doing, I'm randomly picking any index, then I am taking the original label, then I am doing the prediction. And the prediction is in the model, I am feeding the X test, and then I'm plotting the test image with grayscale, and at the title, I'm printing what is the original level and what is the predicted level. And then I'm doing the axis of and simply plotting the image. So now let us see. So you can see that you feed an image of 9, your original label is 9, and your model prediction is also 9. Let us see for another case. Your original image is 7, and original label is 7 too, and predicted level is 7. So this is a 9, and you are doing correct classification. And if you want to see for 100 such cases, so I have just wrote this particular thing, this whole thing in a for loop 100 times, so that it will create a mesh of 10 cross 10. Now you will be able to see for 100 images. So I just have run a for loop, the same code using for loop. So it will run for 100 times and it will create a 10 cross 10 grid. So now let us see. So this is the image of 1. You are doing correct classification. Majorly you are doing correct classification. Then, yeah, mostly all are correctly classified. Yes. So yeah, over here you see, here we can see there is a misclassification that you have done. So original is 5. The image also seems to be of digit 5 only, but your model is doing misprediction. So that means over here in this case, your model fails. You are predicting it as 9. Okay, so any such cases are there? So all are correctly classified so far. Yeah, all are correctly classified. And so this is where you are trying to see all the data, all 100 data, initial 100 data, and you want to see that whether you are doing correct classification or not. Now, if I just want to see the misclassified cases, that means the misclassification part, where your model is actually not able to classify the correct labels. So for that, I need to calculate the indexes and which is not equal to the Y prediction. So that means we have original test labels and we need to choose only those indexes where Y test is not equal to Y prediction. That means you are doing misclassification. And for those indexes, I will see the images. So let me plot. Yeah, so you can see this is a confusing case. The true level is 4. You are predicting it as 9. Eventually, many of us write 9 in this fashion as well. If you are in a hurry, you may write 9 in this fashion as well. So over here, you can see the true is 4. Your prediction is 9. So this somewhat looks like 9 as well. Another case, true is 3, but your model seems to predict it as 5. So that means even though these are mistakes, but these are kind of rational mistakes where the model is purely fooled by the data. And then in this case, you can see this is a 7. This true level is 2. This is the image of 2 that they are claiming. Your model predicts is as 7. But in general, it has some similar characteristics as 7 as well, because many of us write 7 in this way as well. Right. So this is how you can investigate all the possible way to analyze a deep learning network. Many of the people just train a model, test it with the test data, and just tell that I got this much accuracy. But that is not the end point. You can do many more experimentations to understand that how your model has performed by checking the individual results, by checking how what sort of misclass, why it has basically done the misclassification by just seeing the samples which have been misclassified, right? So in this way, you can investigate the things. So this is so far as the LeNet-5 architecture is concerned. So I will show one other simulation that is for VGG16. So the rest part will be same. Only the model part I will change. And the rest of the things will be same because we are training on the same data set. We will be testing using same code. It is just the model part that is basically changed. And we have to see how the model has been changed over here. So I can just start running this particular snippet. So we are training, we are loading the MNIST data. We are first importing all the libraries, then loading the MNIST data. Then we have to create the model. And this is how the VGG16 model looks like. Traditional VGG16 model looks like. You have to keep in mind that VGG16 was trained on ImageNet dataset, and the dimension of the images in the ImageNet dataset is 224 cross 224 cross 3. But in our case, the dataset that we have, MNIST dataset, here the image size is 28 cross 28 cross 1. So that means the image resolution is quite poor, right? And the images are very small in size. So I will simulate the VGG16, but I will cut off some of the layers because that is not required for this very small image. You can understand the original paper that has simulated VGG16. They worked with 2 to 4 cross 2 to 4 cross 3. That means uh, at least 8 to 9 times higher the image size in the original VGG16 paper, as because we are working with very small data. So that is why I will chop off some of the intermediate layers, but I will comment it out. You can just uncomment them and you can train your own VGG16 using that. So now let us start doing the simulation. So first we have 3 cross 3 convolution with 64 number of filters. So again, we'll be using sequential method to write the code. So first is on 2D, number of filter is 64. So I have written 64. 3 cross 3 is the kernel dimension. So 3 cross 3. Activation is ReLU. Padding is same. And input size is 28 cross 28 cross 1. As because the data set that we are working with has this shape of input data, or the image size is this one. Then we have another convolution layer, con2D, 64, 3 cross 3, activation ReLU, padding same. Then we have pooling layer. So I have kept max pooling 2D, pool size is equals to 2 by 2, and stride is equals to 2 by 2. That is very general thing. Then the same thing, only the change over here from this point to this point is 128 number of filters. So I have just put the same 128 number of filters, rest of the parameters are just the same. Then again we have pooling layer. So I have kept a pooling layer. Then what we have, again 3 cross 3 convolution in 3 layers subsequently. The main change is the number of filters have been increased from 128 to 256. So therefore, I have written con 2D 256. Rest of the parameters are same and it is repetitively added 3 times. The last part represents 3 cross 3 convolution with 512 filters. So that part I have just commented out because we do not need such big VGG net to classify the MNIST data. However, you can uncomment this and train your model with this specification as well. That is not an issue. And then over here, what we have after last pooling layer, likewise, we have seen in case of AlexNet that we need to flatten the layer, flatten the output. So I have taken flatten, and then I have to put the dense layer with 4096 neurons. So this is a multi-layer perceptron. Another multi-layer perceptron, I can add dropout layer, which acts as a regularizer. And then at the last layer, I need the classification to be done. And as because we had working on 10 class classification, so thereby my number of neurons in the last layer would be 10 and the activation would be softmax. As because softmax basically give you the probability distribution of the class belongingness of the input image data. Whether input image belongs to class 1 or class 2. Based on that, the probability of that particular index would be highest among all the 10 entries. And after that, you can print the model summary. So let us simulate the model. So you can see that total number of parameters is huge. In case of LeNet, if I just show you, in case of LeNet, total number of parameter was 1,64,506. In this case, it is 2,79,97,898. So that means huge number of parameters. And you can see that model size is 106 MB in case of VGG16. In LeNet, it was in the order of KB, right? So this is a very detrimental thing in the case of VGG16, that it is a very huge network, comprises large number of parameter, and so as the storage size as well. You can see the storage size has grown up from KB to MB. Fine. Now again, the same thing that uh, optimizer is Atom, loss is categorical cross entropy, metric is accuracy, and then we are training with we are doing model.fit to train the model with training data with epoch, let's say 15, batch size I can write 20, so it would be a fair comparison. Then batch size is 128 and validation split is 0.2. So that means 20% data will be taken from these training samples to validate the model to see whether you are doing any sort of overfitting or not. So let me hit the run button. So now let us wait for 20 epochs. It would not take much of a time, I guess, because we are running on GPU. Okay, so we have reached epoch 20. So now we can see the plots. So you're at the last epoch, you got a training accuracy 99.53 and validation accuracy as 99.01, which is pretty good. Now let's see the test error, which matters the most. So test accuracy is 99.14, which is also quite good. Now we can plot the confusion matrix. And here you can see that out of 980, LeNet in class 0, if you remember, it was able to correctly classify 975 samples. VGG16 is doing better, much better, 978. It is doing only 2 misclassifications. But at the same time, here for class 1, both of them are performing, even VGG16 is degraded by 1. So 1131 is correctly classified. In LeNet, it was 1132. In class 2, 1026 for VGG16. In class 2 for LeNet, it is 1021. So this sort of analysis you can do at your own. And this is the normalized version of that. We just have taken normalization. Okay, now we can see the predictions. So over here, you can see the image is 7, true is 7, so as the prediction. True is 2, prediction is also 2. Likewise, so you can just plot and check that whether you encounter any misclassification part or not. But already for misclassification, I have already specifically wrote a code snippet that we have previously also ran, which is like this. So you see, this is true is 5. It is predicting it as 8. So probably it is confused because of this part. As because there is some curvature at this particular position. Again, this particular image is again incorrectly classified. True is 4, but it is model is confused between whether it is 4 or 9. So it is predicting as 9. Okay. So this is true is 5. It is predicting it as 3. Then this is true is 3 and the model VGG16 is basically predicting it as 5. So this is how you can actually simulate the deep learning architectures and investigate each and every nitty-gritty informations about the neural network model, starting from the training cards, testing accuracy, confusion matrix, visualization of the classification of data, as well as specifically the misclassified samples. Okay. So with this, I think we can stop the session. If you have any query, you can ask. Otherwise, we can stop the session here. And I think tomorrow also there is a class, whether they have mentioned or not. Yeah. So October 6, Sunday from 4 to 6. So there will be another class from 4 to 6. Sorry. Yeah. From 4 to 6, October 6, there will be a class that is basically done by the other TA. And I will be taking another class tomorrow from 6 to 8. Yeah. So there will be another class tomorrow. So I
Hello,
hope that, yes.
sir. GitHub links how to
Yeah,
link.
GitHub link. So I have given, so I can show you. So go to the uh, course web page, then go to problem solving session, then problem
Okay.
solving. You go to the sheet, Google Sheet, and then you see that there is a GitHub link is already there. You can go to the GitHub link. So week 2 में मैंने जो करवाया था, that I have uploaded. So today what I have discussed, I will also upload these things in the GitHub repository. So the link is already given. You can access the materials from this link.
Okay, sir.
Okay, so I hope there is no further query, I think. So we can stop recording.
Okay, thank you.